Computational, test 2, computational problem number 3. This is one. I'm going to try to go through this very quickly without too much extra explanation because you guys have seen every bit of these pieces before. So we have an infinite charge plane, we have an infinite wire, and we've got some sphere that's sitting out here. When we look at our top view, what we're looking at is here, here, here. We've got a distance d between these two, and we've got a distance d between here and here. And we are asked to calculate the electric field at the point in the center here, which is just at d over 2 from here. So I'm going to go ahead and choose my axis here. I'm going to go ahead, let's do, okay. So let's do this. Let's go X and Y. What the heck? Okay, so what do we know? We know Gaussian surface here. Around here, I'm going to use a little square. We don't need to use a square. It could also be a cylinder. Doesn't matter because we aren't going to bother calculating the area. We just know that this is an area A. We know that there are 2A on each side. We know we have 2AE0 equals charge enclosed, which is, sigma. I did forget to write that, didn't I? Sigma A over epsilon 0. Sigma A over epsilon 0. And I know that this leads me to sigma over 2 epsilon 0. Now, I need to look at this and decide what direction it is. This is positive. We don't know what sigma is yet, but if sigma is positive, this is positive, which means it is normal to the surface here. So for our purposes here, it is in the y hat direction. Okay, so we are done with part A. Or I shouldn't say part A, with the first part. E equals sigma over, I'll say E1, 2 epsilon 0 y hat. Oh, and the other part, of course, is we're going to use superposition, right? All three of these individually have symmetry that allows us to use Gauss's law, and we are then going to superimpose all three of them to get the electric field here. So at y, and does this depend on y at all? Does it depend on x? No. So at any point here, the electric field due to this, due to that infinite sheet is equal to this. So that's E1. E2, let's go ahead and look at our wire. Our wire is here. I'm going to have some Gaussian surface here. Okay, and I have a charge density lambda on that. It's a linear charge density. So if I have a height L, I know that lambda L is my charge enclosed. So lambda L over epsilon 0 is the charge enclosed over epsilon 0. And I know this is equal to E dot dA, but E is constant on this surface here, and once again, by symmetry, it is normal to the end cap, so I am ignoring the end caps, so all I need to worry about is this cylindrical surface, and I know that that is E0 2 pi RL, and that's that. So, what is E0 then? It's this divided by this divided by 2 pi RL, L's cancel, and I have E, oh, actually there's one more step. So I'll go ahead and do this. E, I'm going to call this E2 instead of E0, I'm just changing my name, equals lambda over 2 pi R epsilon 0. And then the question is, what direction is this? Well, it's in the r hat direction from this spot right here, which is at d over 2. So, it is, E2 of some point P at some taking too long to write down the vector stuff. So just remember that if some vector r from point from point from point 1 to point 2 is going to equal x2 minus x1 in the x hat plus y2 minus y1 in the y hat, and we've got no z hat here, so I'm not going to worry about it. I'll put that around where you can see it. Okay, so this is what we need to worry about. So what is that for our wire here? Our x1 is minus d over 2, so this is going to be a plus d over 2, and our y1 is d. So we have a minus d. So this is yeah, let's go ahead and do that. So at point P, this is P sub x plus d over 2 in the x hat is the r plus P sub y minus d in the y hat. There are other ways you can do this, but this is the way I'm choosing to do it. And then I'm just going to, and this is going to be over the, well, I'll just do it this way. Px plus d over 2 squared plus py minus d squared square root. So that's just r. So this is basically saying r hat is equal to r divided by the magnitude of r. Okay, which you guys know, and I believe it's on the equation sheet too. Okay, so I'm going to go ahead and leave that like that. Actually, yeah, let's go ahead and leave that like that. Okay, so that's our wire. Now we've got this right here, and in case you guys didn't remember, let's see. So we have a Gaussian sphere, so E dot d. I want to leave this, so all right, I'm just going to squeeze this in up here. E dot dA equals E0 4 pi r squared, and that also equals the charge enclosed over epsilon 0, but the charge enclosed is just rho 4/3. I'll call this R1 so we don't confuse it with the R that's actually the R of this sphere. Rho 4/3 pi r cubed. Okay, so 4/3 rho pi r cubed equals E0 4 pi r1 squared. So what is E? E is equal to, I got no place to put it. Okay, I'm going to put it over here and I'll move this. Okay, so E equals, excuse me. Excuse me. Okay, 1 over 4 pi r1 squared times rho 4/3 pi r cubed. And we're just going to do some little really simple algebra with that. And we're going to get rid of that, we're going to get rid of that, we're going to get rid of that, we're going to get rid of that. And we're just going to have E equals rho r cubed over 3r1 squared. Does that look funky to you guys? Oh, yes. It does look funky, but it should look funky, so it's okay. And I forgot an epsilon 0. So there's an epsilon 0 underneath here, and epsilon 0. Okay. All right. So this is now the E of the sphere. So the E of the sphere, so that is E3 is equal to rho r cubed over 3 r1 squared epsilon 0, where r is the diameter of our the radius of our sphere itself. And once again, what direction is this in? Well, it's in the r hat direction, which is exactly the same as this, except that in this case, it is p sub x minus d over 2. And everything else about this expression is exactly the same. So p sub x minus d over 2. Okay, now, what's this p sub x, p sub y? P sub x, p sub y is any point in space. We can now calculate this field, but we're going to do it for a specific point. That specific point has a p sub x equal to 0. So p sub x equals 0. And p sub y is going to equal d over 2. Okay? And that's just basically the coordinates of that point right there. And so now all we have to do is put that into this thing, and we're going to be done. So I'm going to erase our drawing. I think you guys have that in mind right now. Okay. And so what do we have? We have this one here. So our r hat for E2, I'll go ahead and just call R2 hat equals p equals d over 2 x hat plus d over 2 y hat over square root of d over 2 plus d over 2, each of these things squared. So that's going to equal d2d squared over 4, the square root of that, which is going to give us, that's the numerator there, I'm sorry, the denominator there is 2d squared over 4. So I'm just going to take care of a few steps at once here, and what do we have? We have 1 over the square root of 2 x hat plus 1 over square root of 2 y hat. And then same thing for the, let's see, this is R2, so this was from the wire. We're going to have the exact same thing in the other dimension, except that, I'm sorry, for the other field, for the field due to the sphere, for E sub 3, our R3 hat is going to be exactly the same as this, except we're going to have a minus sign here instead of a plus sign. So we can now write the expression for the entire electric field. So I hope now that I've just erased the information I need. Let's see what we got. Okay. All right, so this E3 was minus 1 over square root of 2 x hat plus 1 over square root of 2 y hat. And this is 1 over square root of 2 x hat plus 1 over square root of 2 y hat. And so our entire field, all we need to do is add these up per, in each dimension, in each direction. So our E total is going to equal, let's go ahead and start with positive, lambda over 2 pi r epsilon 0. Yeah, I'm going to go ahead and write it out like this, even though 1 over square root of 2 minus rho r cubed over 3r1 squared epsilon 0, 1 over square root of 2, and this is the, I'm going to go ahead and write out them, each individual component because I don't have room here to put them together like that. Okay, so that is the x component, and the y component is just E T y equals sigma over 2 epsilon 0 plus rho r cubed over 3r1 squared epsilon 0. Why am I wanting this to be negative? Because why was that? I've erased too many things along the way, so I can't remember. But this should have been negative. It was our p sub y for each of these was d over 2, and the expression for r is p sub y minus d. So that should have been a minus d over 2, which should have been a minus 1 over the square root of 2 if after you run through all the things. So I'm hoping that's what I had written and erased. If it isn't, I made a mistake when I did that, but these are, I'm just going to do it like this. I'm going to make it minus 1 over square root of 2. Yeah, we're all right. Okay, minus lambda over 2 pi r epsilon 0 1 over square root of 2, and all this is in the y hat. And we are done. That's it. That's all I asked you for. Right? What is the electric field? E at a point that is centered between all three objects in the YZ plane. So, there you go. Done. I apologize for taking so long with that. I can't, once I start feeling like I'm lecturing, I can't help but do everything. I should try to do one just absolutely silently. Oh, I could try that. Absolutely silently and then narrate it afterwards. So, if necessary. And then that way you'd see how long I think a problem like this would take. And I would say you guys should probably take like twice as long just because you haven't done them as much. Okay.